Okay, relative solubilities, not hard. Okay, there's basically one way, well, two ways this question can be asked. Which of the following compounds will have the greatest molar solubility? You might also be asked which has the least. Okay, and then usually in these circumstances we'll be given the KSP value, so this should be KSP, that should be over there. Okay, in some circumstances, such as this one, for reasons that we'll talk about later, you can actually just compare the KSP. So if you're looking for the greatest molar solubility, will that be a large KSP or a low KSP? Okay, large molar solubility will mean large KSP. It will be more product favored. So in this case, we could just say barium chloride has the greatest molar solubility because it has the largest KSP. So in summary, sometimes, and we'll explain what the sometimes means later, comparing KSP directly can determine which has the greatest or the least molar solubility. Okay, and I do want to remind you that when we're talking about molar solubility, mathematically that is the X that we've been calculating in previous problems. The textbook calls it S, but it's the same. Okay? So let's look at a circumstance where you cannot just compare KSP. So you guys may remember AGCL came up earlier. I just noticed, this is my second take of this video, I just noticed that on a previous slide its KSP is something to the negative 73. This is the actual value, that's I'm not sure where the other number came from, but it doesn't matter. Okay, so this time we cannot compare KSP. So I want you to think about why that might be while I write out these reactions. Okay. The reason we can't compare KSP in this case is because in this case, KSP is related to X by mathematically different expressions. So remember, because AgCl breaks into two ions, that its expression will be KSP equals X squared. Conversely, because Ag2CrO4 breaks into three ions, it will be 2X squared times X, which is 4X cubed. So when we actually solve those expressions for our X value, we might see a different relationship. Okay, so over here we get X equals 1.7 times 10 to the negative 5, we'll call it molar or moles per liter. Over here, X is 1.3 times 10 to the negative 4 molar. So if it's a well-written question, okay. If it's a well-written question, the one with the greater molar solubility, it will phrase it so that if you don't remember to do this calculation, you will just pick the one with the larger KSP value, and you'll be wrong. Because when you actually do the calculations, you'll find that it's the other one. Okay? So they're not going to write it in the way that you're accidentally going to get it right. Okay, so we would say because this one has a larger X value, it is more soluble in water. Okay, so the reason again that we had to do the math was because they break into different numbers of ions. So if you're going to summarize that trend, we would say if the compounds break into the same number of ions, we can compare to... Baba, can you please stop? To determine which has greater molar solubility. Otherwise, if they break into different numbers of ions... No! Asher, Baba, please stop doing that. Otherwise, I have to calculate X using their respective expressions for that. Okay, so let's do an example. In this case, ion 2 oxalate breaks into two ions. You guys can see that. This guy, copper 2 per iodate breaks into 3 ions. So we're going to have to do a little bit of math here, but it's easy. And again, you do not have to do the Rice table if you remember the expressions. So when it breaks into 2 ions, it's just x squared. And when it breaks into 3 ions, it's 4x cubed. And from there, we can find, I'll do this in the same order. We can find x. Okay? The answers for this one are on the next slide. You guys can see their work in the textbook, and again, they call it s. So they have s squared and they have 4s cubed, and then they solve for s. And again, in this case, they're asking, in this case, they're asking for smallest molar solubility. That's like the most annoying mistake, is to misinterpret the question. So we would think, smallest KSP, which is this one. But again, if you actually do the math, you find that this one has the lowest molar solubility in terms of the molarity. So it's iron 2 oxalate. Okay. So here's another problem. This one's actually 40B. It's the next one on that problem. Again, smallest. Okay, in this case, they both break into 3 ions. And granted, the silver, the cation on the left is the 2, has double, and the anion on the right has double, but that doesn't change the math. They still both end up being 4x cubed. So we can just compare KSP. Smallest, so we're looking for the smallest KSP, so Mn, OH2. Manganese 2 hydroxide will be our least soluble. Okay, and you can see their explanation here. For you guys to practice this, I want you to do the sister problem for number 40, which is number 39, parts A and B. And then check your answers, please.